So let's get that going. Feels weird to seeing the 6 SOAR pictures. Okay, I feel like I'm talking to a bunch of portraits. Okay. Okay. Thank you for.
I didn't know if you wanted them on because of how it affects the recording.
Oh, okay. When it's a screen share, then you could have your cameras on. Yeah, because when I'm just using my regular video feed without a screen share and it's webcam pointing at the board, that's when you guys need to have your cameras off. So okay, all right. So thank you for creating a nicer teaching environment. Okay, thank you too, Samson. Okay, the room you're in is really white.
He's in the math center.
Yeah, sorry, it was like really bright. Okay.
I have a cat in the background.
Oh, okay. Oh, thank you.
All he does is sleep.
Yeah, it looks like it's a big old black, unidentifiable blob.
Yep, that's the cat.
Okay. Well, that's also what my dog looks like. So,
the cat is 16 years old, so he's earned his right to sleep all the time.
Oh yes, definitely. Well, you know, they do put up with a lot. Okay, so here we go. So the only thing from last section that I did not get to, I'll just go ahead and do now. So a 2D problem for Poisson's equation. So we have minus Laplacian of u in 2D is equal to some given function f. And for convenience, the domain will be the square, 0 to 2 pi. And we're assuming that u is periodic in both x and y. So because u is 2 pi periodic in both directions, okay. Let's see. Then we can express as a Fourier series. So it's a double summation over indices k and l that are used to identify frequencies. So we have these two-dimensional complex exponentials, and then Fourier coefficients that have two indices. And actually, I'm going to fill in the formula for the Fourier coefficients. All right, so you saw this factor last time, 1 over 2 pi, but because it's two-dimensional, it's 1 over 2 pi quantity squared. And it's the integral over the entire square omega of the minus exponential f of xy dx dy. All right, so those are our Fourier coefficients. And then we also, and since u is going to be periodic, it will have the same kind of a Fourier series. So exactly like this, just with u of xy, then we have Fourier coefficients u hat with indices kl. So to figure out what the coefficients of u have to be, I can just I could take a Laplacian of a Fourier series. So that's what I do. So I have my Fourier series for u, and I'm taking minus Laplacian of it. Now, so what will happen when I take second derivative of an expression like this with respect to x? Then I'm going to multiply by ik squared. But I is the square root of minus 1, so I'm actually multiplying by minus k squared. Similarly, if I take a second derivative with respect to y, I can be multiplying by minus L squared. And the Laplacian, you add them together. So that's why when you are taking minus the Laplacian, you're just multiplying the Fourier coefficients by k squared plus L squared. Okay. Okay, actually, I'm going to fill in a little of what I just said here. That the second derivative with respect to x. All right, so I'll just describe a Fourier series there. All right, so in this case, I'm multiplying by minus k squared. Okay, and then similar for uyy. So that's what leads to this. So here we have minus Laplacian of u, but that's supposed to equal f. So now I need to take this Fourier series and match it with this one. And we have a double summations in common. And we also have the complex exponentials in common. So I need this to equal f hat KL. So that lets me solve for the Fourier coefficients of u in terms of the Fourier coefficients of f. I'm just dividing by k squared plus l squared. As long as, of course, k and l are not both equal to 0. Now, what about the case where k and l are both equal to 0? How do you handle that? Well, we need f hat 0, 0 to be 0. It cannot be part of this. Now, u hat 0, 0, I can include it in a solution. Actually, it doesn't matter what I choose it. Because if you consider a case of k and l both being 0, well, this would be e to the 0, which is 1. So in other words, the 0, 0 coefficient is just a constant term. It doesn't depend on x and y. So if I look at u here, if I add a constant to u, it's not going to affect this because I'm taking derivatives, and derivatives of that constant would be 0. So it turns out the solution is not unique based on the conditions given here. There's an infinitely many solutions possible where it all differ by it's kind of like a constant of integration. But if f has a constant term, then that's a problem. And the reason why is, suppose I have a constant term. I need a function whose Laplacian is equal to a constant. Well, a function like that's not going to satisfy boundary conditions. It's not going to be 2-pi periodic. So that's why we have this condition for the existence of a solution that f hat 0, 0 has to be 0. Because there's no way to take a Laplacian of any term in a Fourier series and get a constant. It's just not possible. Okay, so when you have a PDE with constant coefficients on a rectangular domain and periodic boundary conditions, that's a very easy PDE to solve, as this example shows. So we actually have a formula for a solution. Now, for a numerical approximation, we would have to we'd have to cut off the series at some point. So it's going to be an approximation, but that would still be very accurate, especially in a case where f is a smooth function. This is why I really like spectral methods, because we can get solutions, very accurate solutions in cases like these. And it comes from a fact that these exponentials, e to the I kx plus ly, these are eigenfunctions of Laplacian. You take a Laplacian of this function, you get that function again times the constant. So that's an eigenvalue eigenfunction relationship. So anytime you know the eigenvalues and eigenfunctions of your differential operator, then PDEs always become very easy to solve in that case. But that generally happens only in nice domains with constant coefficients. Although I have been working with some students on trying to accomplish the same thing for other problems, and had some success in one space dimension due to students such as Elise Garon and one Sarah Wright did that for her undergrad honors thesis, and I've had students working on it on 2D. For example, that's what Chelsea's been working on, and we're discovering just how hard the two-dimensional version of that problem is. But we've learned a lot about it. That's really the goal of my research program, is to try to extend the ease of solution using spectral methods to a wider class of PDEs than this narrow category here of rectangular domains, constant coefficients, periodic or homogeneous boundary conditions. Okay, so any questions about how this example was solved? Now, in Matlab, how you would go about solving this, like if you had a matrix of values for f on this on a two-dimensional on a grid for this square, so x and y values, what you do is you can use Matlab's function for a two-dimensional fast Fourier transform. It's FFT2 to get the coefficients f hat. So once you have those, then you would divide them by the appropriate sums of squares, k squared plus l squared, and then you would use MATLAB's IFFT2, the inverse two-dimensional fast Fourier transform, to go back and get to get u of xy. Okay. And we'll take that up with one of the homework problems, I believe. Actually, I want to check on this. Okay. Courses 721. I think it's well, it had to be one of the problems in homework 2. Let's see. Okay, there's a one-dimensional problem. It's problem 5. That's in homework 2, where you use a one-dimensional fast Fourier transform to come up with a solution. It's Poisson's equation for that. So it's the same idea as what you see here, but stripped down a bit because it's only one dimension. Okay. So that's periodic boundary conditions. I have non-periodic. Although, actually, one thing I want to point out to you. Okay, this is just gonna drive me batty. So I have to vent, and since actually most, or I guess all of you, well, yeah, all of you in some capacity are involved with teaching. Because the reason I'm down here is to teach Math 465-60, and we have students enrolled at both campuses. So I teach in person up in Hattiesburg, but I want to occasionally teach in person down at the coast. That's why I'm here. And I told them on this day I will be down here. There are 4 students enrolled here, and apparently I might only have at most 2 of them present. So why did I come down here? But anyhow, we'll see how it goes. How many actually are in the room? Okay. Now, what about case of non-periodic boundary conditions? So in that case, it's not advisable. Well, okay, depends on the boundary conditions. Like if you have homogeneous Dirichlet boundary conditions, you could use a Fourier sine series. Or if it's homogeneous Neumann boundary conditions, you could use a Fourier cosine series. Or you might have different, like non-homogeneous boundary conditions. where a Fourier spectral method might not be the best idea. So I want to show you an alternative to a Fourier spectral method when you don't have periodicity, because when a function is not periodic, then you take like for instance 2 pi periodic extension, it's going to have discontinuities, and that's going to be a problem for spectral methods because the Fourier series coefficients go to 0 very slowly in that case. So what we're going to look at is spectral methods that rely on ordinary polynomials, algebraic polynomials, instead of trigonometric polynomials. So with Fourier spectral methods, in the periodic case, we use equally spaced points on our grid. But when you don't have a periodicity, if you're going to use polynomial approximation, you don't want to use equally spaced points. And there's an example that I've shown in certain classes. This function is called Runge's example. This function on the interval -1 to 1. If you try to use a high degree polynomial to approximate this function, then you get some very large errors. And I'm actually going to flip over to Matlab and show you just how bad it can get. Okay, hold on. I'm gonna close some applications down. Okay. Okay. Let's see, get the screen share going again. All right. So what I'm going to do is okay. I'll post this diary afterwards, but so polynomial interpolation of this function 1 over 1 plus 16x squared on the interval -1 to 1. Okay, so I'm going to find equally spaced points -1 to 1, and I'm going to use 11 points altogether. I'm going to make it a column vector. So 11 points will give you a polynomial of degree 10. So then my y values would be just plugging into a function. And then I'll compute the interpolating polynomial using MATLAB's function polyfit. Okay, so now I have my polynomial, or at least the coefficients of it. Then what I'll do is I want to plot the polynomial and the function on the same graph. Make sure I don't have any figure windows open. Okay, next, I need to find a vector of more points. I'll use like 1,000. Okay, so now I'm going to plot, actually I'm going to find a function handle here for my function, just for convenience. So now I'm going to plot x2 and then f of x2. So this is the true function. Okay. And then I will superimpose on it by evaluating a polynomial p at these many equally spaced points, and I'll use a red dashed curve. And that did not go so well. We have these enormous errors over here. Okay. All right. So now, as you can see, this red polynomial does intersect with the graph of a function at various points. Like if I were to plot the interpolation points, I use black circles, and you see the interpolating polynomial and the actual function do meet at those points. It's just because it agrees at these points does not mean it's going to closely agree everywhere in between, certainly not at the edges. So we need to try something different than equally spaced points. Okay, so I'll show you what we can do is use a Chebyshev points. So if you take the unit circle, the top half, and you have points that are equally spaced in the angle theta, and then you take cosine of those points, so angles from 0 to 2 pi. If you take cosine of those angles from 0 to 2 pi, then you get values along the x-axis from -1 to 1, and these are the Chebyshev points. So what I'm going to do is I'm going to use these points now, and as interpolation points for Runge's example, and we'll see how well that does. So I want to use the same number of points, 11. So I'll use capital N equal to 10. So I'll go back to Matlab. Okay, so Chebyshev points will be equal to, so the formula is cosine of pi j over n. So pi times j. J is going to range from 0 to 10. Okay. So, and I'm transposing because I want column vectors for these. Okay. So then what I'll do is do polynomial interpolation again with these points and plugging into a function. It's also degree 10. And then I'll evaluate that polynomial, and I'll use a black dotted curve. Okay, I don't know how well you can see this. I'm gonna change the appearance of the graph so that it's easier to see. Make the curves thicker. Okay, much better. So now the black is the approximation using Chebyshev points. And there's still error, of course, but it agrees much more closely than with the red one that's based on equally spaced points. And I can try to show you I use green pluses. Hopefully it'll show up. Okay. Okay, I'm gonna try I'm gonna delete some. Well, first I can make this bigger. Okay, because so black circles, those are equally spaced. Now I'm gonna get rid of, okay. Actually, I'm gonna save this. So I can post it in Canvas later. Okay. Okay. All right, so I'll get rid of this. Okay. And I'm gonna get rid of the equally spaced points. Okay. And then I'm going to plot the Chebyshev points again using green circles. That might be easier to see. Oh, yeah, you can. So we have one in the center here. And notice there aren't any more until down here. And then if I pick a side of a graph and keep going, notice they get closer and closer together. Like these two are really close together. So with equally spaced points, you tend to get larger errors toward the boundary, as we just saw in this example. But Chebyshev clusters points near the boundary. And that's the artifact of taking equally spaced angles, but taking cosine of them. The graph of cosine goes more and more vertical as you get to the sides. So taking cosine of those angles that are equally spaced, but on those edges, leads to x coordinates that are closer together. Okay, so that's why Chebyshev points tend to be clustered near the boundary. All right. So now what I can do is I can represent the interpolating polynomial in Lagrange form. So Lagrange polynomials, you may recall from other classes, are polynomials that if I plug in any of the interpolation points, any of these Chebyshev points that are equal to 0 when k is not equal to j, and it's equal to 1 when k is equal to j. And this formula is designed to ensure that. Like if I plug in x equal to like xi, where I is not equal to j, then one of these linear factors will be 0, and the whole thing will become 0. Whereas if I plug in x equal to xj, all these factors cancel, and you get 1. So then, what I can do is approximate the derivative of my function by taking a derivative of a Chebyshev polynomial, of an interpolating polynomial, and plugging in xi. Now that's actually the same thing I did last time with a periodic case. I had a trigonometric interpolant of u of x, and I took its derivative and plugged in the point that I wanted the derivative at. So it's the same principle here. You take your function, you approximate it by some kind of simpler function, like a algebraic polynomial here or a trigonometric polynomial last time. Take its derivative at the point of interest. So again, the approximation of a derivative is the exact derivative of the approximating function. And that's going to be something that has this form, because here, this polynomial is a linear combination of the u values. You take a derivative, that again will be a linear combination of the u values. But what are the derivatives of these Lagrange polynomials at the xi's? Well, it turns out there are formulas for these things. These are not easy to prove. In fact, I actually haven't been able to do it, and I am somewhat embarrassed to admit that. Although it could be something where I'm just not thinking of a right approach, because for something like this, you find the right approach, and it might actually become relatively easy. But if you don't find an approach, then it's like it might as well be impossible. But this is a formula for derivatives of Lagrange polynomials at these points, and we have separate formulas for where I is equal to j versus not equal to j. So what you can do is, what we have here is differentiation matrix. That the derivative of u at xi is equal to the ith element of this matrix vector product. So just as I had a differentiation matrix in the periodic case that had all those cotangents, this is a differentiation matrix for Chebyshev interpolation. And the matrix turns out to be this. Again, these formulas are heinous to try to prove. I actually haven't found the proof, like in a reference. They're worked out somewhere. So once again, this is a full matrix, but there are these patterns to the formulas. Well, unlike the periodic case, it's actually not a skew-symmetric matrix. But for one thing, it's not equal to 0 on the boundary, or sorry, on the main diagonal. Okay. So if you have a vector of values of u, then you can multiply that u vector by this matrix, and you get values of u prime at those same grid points. If you multiply by d again, then that's second derivative. So you can take powers of this matrix and get differentiation matrices for higher order derivatives. Yeah. Now, this is not so efficient because you're doing a matrix vector multiplication of a full matrix. That's order n squared operations. But you can also, it is also possible to use the FFT. And the reason for that is you can perform, even though U itself is not periodic, if you evaluated Chebyshev points and you do what's called an even extension, so you're reflecting it across the y-axis, and this is what that extension looks like, and you can carry out a fast Fourier transform of that. So because when you do a reflection like this, the resulting function, the even extension, is continuous. So you can take a Fourier series of it. Also, it would turn out to be 2 pi periodic. That's the important thing. Okay, so then when you take a fast Fourier transform of that using 2n total points, because we have 2n total points here, then you could take its derivative, like you normally would for a Fourier series, and then take the inverse fast Fourier transform, and now you have a derivative, and then you basically undo the even extension. So that's what this formula is. So, and the reason why we had to divide by this factor of minus square root of 1 minus x squared is because when you're making its change of variable, you're changing, you're basically performing a change of variable x is equal to cosine theta. When you're taking the derivative after taking FFT, you're not taking a derivative with respect to x. You're taking a derivative with respect to theta. But the derivative with respect to x is a derivative with respect to theta times d theta dx, which is this. So that's why that factor has to be included. Yeah. And this is the rest of the process. Now, I should mention that this procedure for computing Chebyshev derivatives efficiently using a fast Fourier transform, I got from a book by, actually he's my, I guess, academic brother, Nick Trefethen, who's a professor at Oxford, actually one of the most famous numerical analysis people in the world. And he wrote a book on spectral methods in Matlab, where this is described. Although when I was looking through it in his book, I couldn't help but notice that there were some typos. And it was difficult to see what, I could see that certain things were wrong, but wasn't sure what the right thing should be. So I've reproduced it here as he has in the book anyway, but I can't be certain about 100% certain about the correctness of what's in here because of what's in the book. So I need to quickly add that this is not going to affect you as far as homework is concerned. Like there is a problem concerning Chebyshev differentiation, but for that, you could write MATLAB code that would form this matrix and just use that instead of this FFT approach. But I do need to mention the FFT approach because even though it's fine for the assignment, just in practice, this is not the fastest way to do it. That you can, instead of performing order n squared operations, you can perform order n log n operations using this procedure that comes from the FFT. Okay. Actually, I want to quickly describe, since it came up with this approach involving the FFT. I'll show you the connection between Chebyshev polynomials and Fourier cosine series. Okay. Suppose we have okay. So Chebyshev polynomials are defined as follows. Tk of x is equal to cosine of k inverse cosine of x, where x is between -1 and 1. Important property of Chebyshev polynomials, Chebyshev, are orthogonal on the interval -1 to 1 with respect to the weight function which is actually this denominator we see here. So it's 1 minus x squared to the -1/2 power, meaning that the inner product of two Chebyshev polynomials, which is defined to be the integral from -1 to 1 of Tj of x, Tk of x, with the weight function so that is equal to 0 whenever I is not equal to j, or j is not equal to k. All right. Now, suppose you want to express a general function f of x as a linear combination of Chebyshev polynomials. Because they have this orthogonality relationship, you can do that so f of x is approximately equal to all right, so some coefficients Cj times Tj of x, and the way you get to coefficients Tj, because they're orthogonal, this is true of general expansions of orthogonal functions. Okay. But that's how you get the coefficients. If these are orthogonal in some sense, then you take the inner product of each one of these with f as a numerator, divided by the inner product of that function with itself in the denominator. Those are the coefficients. Okay. But now if I want to take a look at this inner product, okay, so that's the integral from -1 to 1 of cosine of j inverse cosine x fx dx. All right, but now what I'm going to do is make a substitution. And that substitution is x is equal to cosine theta, and that will lead to dx is equal to minus sine theta d theta. Oh, actually, okay. Okay. All right. Oh, I forgot the weight function. No, I didn't want that. Okay. I knew I was missing something here. Okay. Now, when I make a substitution through here to get an integral in terms of theta, well, if x is cosine theta, then theta is inverse cosine of x. So I'm just going to have j theta right here. Okay. X will be cosine theta. And then here I have minus cosine squared theta, and then dx is equal to minus sine theta d theta. But 1 minus cosine squared is sine squared. So now I have 1 over sine theta in this fraction, which cancels with the sine theta here. So all that just goes away. Also, the limits, if x is equal to 1, then cosine, then theta is equal to 0. And if x is equal to minus 1, then theta is equal to pi. So here I'm going to have pi, and here I'm going to have 0. But I can flip the limits by changing the sign. So the minus goes away, and I have 0 to pi. All right. So what we have here, this is a discrete. This is a cosine transform of f of cosine theta because I'm taking the inner products with cosine. So okay. So a Chebyshev transform in X relates to a cosine transform in theta. Okay. So it's pointing out how deep it goes, the connection between Chebyshev polynomials and cosines, because they're defined in terms of cosines. Okay. So if I wanted to compute these coefficients, I could actually use the fast Fourier transform to compute all of these. Okay. All right. So a lot of operations with Chebyshev polynomials can be carried out efficiently by changing to basically theta land and using the FFT. So the efficiency compared to Fourier spectral methods is about the same. All right. Now, I want to show you some examples involving non-periodic boundary conditions and how the differentiation matrix that I showed you earlier can be used. So, for example, here we have Poisson's equation with e to the 4x as the right-hand side, and these boundary conditions. So we're on the interval -1 to 1, homogeneous Dirichlet boundary conditions. So what you do is you if this matrix from earlier, and I'm going to call this dn. Okay, just to make explicit how many grid points we're using here. So I can take this matrix and use it here. Now, because I'm doing a second derivative, dn approximates the first derivative, so I have to square it. Now, be very careful about this. Here I have dn squared tilde, where I form dn squared first. I just square dn to get its matrix for a second derivative. And then I remove a first and last rows and columns. And the reason why is first and last rows and columns correspond to the boundary points. But on the boundary, I already know the solution. It's 0. So we don't need those. But I want to emphasize here you square the matrix first, then delete those first and last rows and columns. If you go the other way, you're going to get a very inaccurate approximation. Okay. So then this right-hand side will include values of e to the 4x, but only at the interior Chebyshev points. So you exclude -1 and 1. So then you just solve this ax equals b problem. You just use backslash for this, and bam, you have your solution u at the interior points, and then you know it's 0 on the boundary. So, so in terms of what you do in Matlab, there's not very much to do here. The most tedious part is writing whatever code you need to form this matrix and then work with it. There are questions about this example? Here's a similar example, except it's nonlinear because we have e to the u. So the right-hand side depends on the solution u. So what do you do in that case? You can't just set up an ax equals b problem and solve it. Instead, you can perform an iteration. So we have this. So the left side is the same setup as before, where you form dn, you square it, remove the first and last rows and columns because we have the same boundary conditions as before, 0 on the boundary. And then your right-hand side will be e to the u, but you set up an iteration, like you can choose an initial guess like u equals 0, because that satisfies the boundary conditions, and perform an iteration. So this is like a fixed point iteration in a way. In fact, if I multiplied both sides by the inverse of its matrix, then it would literally be a fixed point iteration. And then hopefully it will converge. Actually, I believe it would converge in this case. You can also use, for instance, Newton's method for a system of equations to solve this, but that would be a lot more tedious to set up. And in that case, you'd really want to have make sure to have a good initial guess, or it might not converge. All right, so you can combine these with other numerical methods, especially in the case of a nonlinear problem. For this one, this is an eigenvalue problem that a differential operator applied to u is equal to a scalar times u. So we have a eigenvalue eigenfunction relationship, same boundary conditions. So what you would do is you would obtain a matrix dn tilde squared again. So really what you want are the eigenvalues of this matrix. So that's what you could do. You could just use eig to get so the idea is lambda here is unknown. You're just looking for whatever eigenvalues there are. So you can get eigenvalues and eigenvectors using MATLAB's eig. So the columns of the matrix V are the eigenvectors, and then the diagonal entries of L are the eigenvalues. So those are your lambda values, and your U's, your corresponding U's, would come from the columns of V. And then, okay, I have a couple more examples. This is Poisson's equation again, on a rectangle, so a two-dimensional problem, as opposed to the 1D problems that we had. Same domain in space, just for x, both x and y, from -1 to 1. And here's an example function f here, just made up. So again, you solve a system of equations, but to jump from 1D to 2D, you have the same matrix as in the one-dimensional case, that's second derivative with respect to x, and then you take the Kronecker product with identity, first in this order for uxx, and then in this order for uyy. This is the matrix that describes the Laplacian using on a grid of Chebyshev points. So to do this in Matlab, Matlab provides a function cron that's used to take Kronecker products of two matrices. So here you have an n by n matrix. I mean, you take the n by n identity and use cron of this, comma this, and then cron of this, comma this, and then use backslash to solve this system. Now you would form a function f by evaluating it at the grid points, but make sure that this is a vector, because, okay, so I'll make a note here about Matlab implementation. Okay, so given a vector x of Chebyshev points, you can use Matlab's function mesh grid to obtain x and y coordinates of grid points with the same Chebyshev spacing, to evaluate f of xy on the grid. But that now mesh grid returns a matrix of x coordinates and a matrix of y coordinates, but you must reshape into a vector. So before using this system, you reshape f into a column vector. You solve this system of equations. Your solution U is a column vector, but then you could reshape that into an n by n matrix. If, like, for instance, if you wanted to visualize a solution. Yeah. So it doesn't take much for solving these kind of equations to make the leap from 1D to 2D. But as I mentioned, and as Chelsea can attest to, sometimes the leap from 1D to 2D for certain problems is much more daunting. Okay. And finally, here's a wave equation, 2 dimensions, and here we have a source term. And if you let V, the solution, have this form, so this function of t times this function of only x and y, you substitute that in here, then the PDE simplifies and you end up with this. This is called the Helmholtz equation, where you have this additional term, so Laplacian plus this is just equal to f. So this is a sort of problem that you can solve using the same approach as in the previous example, that this is the matrix that you form now, where ln is the same ln as in the previous example, but now it's shifted by k squared times identity. So then you can go ahead and solve this system of equations to get U. Okay. So questions about any of these? Or okay, we have 12 minutes. Questions about anything?
I have a question in Question number 2 on the homework.
Okay. Interesting background, Chandler. Okay, number 2. All right. Okay.
So first is the notation. When you say u equals 0 at 0,1, that means u of 0 is 0 and u of 1 is 0.
Yeah, so it's specifying the homogeneous Dirichlet boundary conditions. Yeah, u of 0 is 0 and u of 1 is 0.
Okay. Then next was, okay, so because this is Dirichlet boundary condition, the system of form will be different from the one you did in class. Like you wouldn't have the right hand side would just be f at the interior points, right?
Yes.
Or the matrix A would be the same thing.
Yes. So the matrix, since you don't have that Neumann boundary condition to deal with, it's just going to be 2 down two's on the diagonal, and then -1's above and below, and then divided by h squared.
Yeah, so that's what I got, right? And then I formed f using this function. Okay, so this is, so we're differentiating, like, because this got confusing. This function here, we have sine phi of x multiplying phi, like the first derivative of phi to the second power, right?
Yeah. Yep.
Minus cos of phi, then this. So I did this and I implemented this. Then you mentioned that to get the exact solution, we just had to integrate twice this function.
Okay. Yeah. Now, so what makes this what makes it interesting, or I guess difficult, to find the exact solution is, yeah, you want to, like, you can think of it as integrating twice, but how you integrate it's like, okay, if you go ahead and fill in phi is 9 pi x squared, if you wanted to just do conventional integration, you could do that, because, like, if you have polynomial times a sine or a cosine, you could use integration by parts. There is an easier way, or I should say less tedious at least, is even if you don't fill in phi here, if you can recognize this as the result of applying the product rule. And the reason why I say product rule is because, for one thing, you have 2 terms, which a product rule produces, and you have sine being a derivative derivative cosine is minus sine, or derivative sine is cosine. So if you think of this as 2 terms where one function is being differentiated and the other is not, like here we have phi xx. So in this term, phi is what got differentiated. Here you only have phi x, therefore it was not differentiated over here. So, and then here, so it's possible to recognize this as the output of a product rule, and then you can figure out, okay, what is a product that's being differentiated? Then that would at least give you minus ux. Then try integrating that, which would be easier, and then you can recover u.
Okay. So because I did, I integrated this, like put in 9 phi of x, and then they did double integration. I guess I made some error doing the integration, but the point was the results I got for the exact solution and the results for the approximate solution was so different.
Oh, okay.
So far apart.
Now, sometimes when I've had prior students work this one out, and then they go ahead and plot their exact solution and then plot their numerical solution. Sometimes even though they're far apart, there's a clear pattern as to how they're different. Like for instance, like a sign difference or something like that.
This one is even order of magnitude, like.
Okay, it could be a scaling factor that's off. And because what's happening is, okay. So what I could do is, and of course this is something that I want to, that I would have a chance to do next week for anyone who hasn't worked it out by then. Just to see what people are doing, see what y'all are doing for your code, and make sure that everybody's good shape. And that includes you too, Caitlin, even though you're at the coast. That we would I would accommodate you as well in that. Okay, so now when you came up with an exact solution, now did you substitute it back in here to verify that's the correct exact solution?
Oh no, I didn't. It didn't occur to me to do that.
Okay, yeah. Make sure you do that before you go any further, because what if your exact solution's wrong?
Yeah.
Okay. I will say that I mean, if you were to plot these things, if the exact solution is a function of reasonable magnitude, it just has some interesting behavior. But so if you get and that means therefore your numerical solution should too. So if your numerical solution is like particularly large or particularly small, then if there's something off with your either your matrix or your right hand side.
So like for n, we can pick any value, right? Because I just pick n to be 9.
9?
Yeah.
Oh, you can pick n to be anything. I'd recommend something larger, just so you, because the more points you pick, the more accurate the approximation will be. Then you can make sure your code is correct. Like maybe
I thought of doing 100, but I felt like I wanted to see what was happening, and it was easy to look at a vector with 9 columns than to look at a vector with 100.
Oh, I see. Okay. Well, yeah, that could be helpful for certain things, but yeah, I don't know if I've tried it with that few grid points, so don't expect too much accuracy in that case.
Okay.
All right. We have a few minutes. Other questions? Okay. Oh, it's probably quick before Chandler actually disappears. Sorry, this is funny. Like all of a sudden, like poof, you're gone. Okay. So I don't have to cover anything for a while, thankfully. So all of you try to move the homework along as much as you can. I know this problem 2 has many parts. So we can talk about them next week. But the more you're able to do beforehand, even if you don't get all the way to an answer, the more productive that time will be. Okay. Stopping recording now.